In this video, we're going to discuss something that is very important to a lot of mathematics, not just algebra, but further on up into calculus, linear algebra, differential equations, and even higher. And that's this concept of a function. In a lot of real-world situations, we observe that one quantity is often dependent on another. We talked previously about variation, how one variable is directly proportional or varies directly with another, or in contrast, one variable varies inversely with another. We can take a simple example like wages for a job. The number of hours that you work in your job directly influences the amount of money that you will receive from working that job. Mathematically, if we want to represent this dependent relationship, we will use a function. And here we have the definition of a function. A function is a rule that takes some numbers as inputs and assigns to each of those numbers a definite output value. The set of all input numbers is called the domain of the function, and the set of all output numbers is called the range of the function. We can also define a function differently in that it is a correspondence, a relationship between the domain and the range, such that each member of the domain corresponds to exactly one member of the range. It turns out that a function is a very specific type of a relation. A relation is also a correspondence between the domain and the range, but in a relation, we do not have this restriction of exactly one. For a relation, it is a correspondence between the domain and the range, so that each number of the domain corresponds to at least one member of the range. I've got tons of examples built in so that we can see what is a function and what is not a function, and be able to more deeply understand these definitions. A function can be represented by a table of numbers, by just words, by a graph, or a formula. We also have something called an arrow diagram that you'll see a little bit later. In everyday language, a function is expressing a notation of dependence. One quantity, the outcome, depends on the value, the input, of another. You can think of a function almost like a machine. How about a donut machine? Consider something as simple as a donut machine. Here we have a great display of donuts being fried and then eventually glazed. And what to notice about this, we have the donuts coming into the hot oil and being fried. So we've got an input of dough for the donuts, and then they ride this conveyor belt all the way around. In the back you can't see because the picture's cut off, until they're over here and we have the finished product of the donut. So we have this machine of an input value and an output value. This is a function. The dough goes in, the function does something to it. It fries it and then makes it yummy and puts sugary glaze on it. And then the finished product comes out and we have our output. So going back to our diagram, a function has exactly one output for every value of input. But something that's not a function, or in more general, a relation, there's an input that has more than one output. So remember, the important thing about the function, each input goes to exactly one output. In the first example, we're going to determine whether each of the following relationships represent a function or a relation. In our first example, our domain is the teams, and our range is the location. So we're talking about baseball teams. We have the A's, the Giants, the Cubs, the White Sox, and the Angels. Tiny little thing here, I shouldn't have an apostrophe for Giants. I know, small things. And then notice there's an arrow connecting the team to a location. So we've got the A's being connected to Oakland, the Giants connected to San Francisco, the Cubs and the White Sox are connected to Chicago, and the Angels to Anaheim. And we must ask ourselves, in this first example, is this a function? If you say yes, why is it a function? If you say no, you have to be able to show where it breaks down, where the problem is. So do we have exactly one output for every input? Each input goes to exactly one output. Each team has exactly one location. So this is a function because each team has exactly one location. Let's flip it around and make our domain the location and our range the teams. And now notice how things are different. Oakland gets mapped to the A's. Okay, not that much different. San Francisco gets mapped to the Giants. Okay. Chicago gets mapped to the Cubs and to the White Sox. And Anaheim goes to the Angels. So we ask the same question. Is this a function? Do we still have the same situation of every location gets exactly one team? In the function words, do we have exactly one output for every input? And hopefully you can see it. There's a problem here with Chicago. Chicago gets mapped to two different teams. So one input has two outputs. This is not a function. We do not have exactly one output for every input. There is one input having two outputs. It only takes one value of input to be mapped to more than one output for this situation to no longer be a function. So we can't have that and call it a function. In the next video, we'll look at these examples and determine whether they are functions or not. Before you move to the next video though, see if you can determine on your own each one of these 4 examples. Do they represent a function? If they do, it's because each value in the domain gets mapped to one value in the range. If they don't, it's because one domain value gets mapped to more than one range value. So this is really going to take some expanding of your brain and thinking critically about each item in the domain and each item in the range, and ask yourself, can I have more than one value in the range being mapped to each of these domain values? And remember, it only takes one, and the situation is not a function. Think about that. See if you can come up with your own reasons, and then start the next video for the solutions.